Today we're going to take a look at section 2.2, describing sets. And before we can even get any depth of this at all, we have to define what we mean by a set. So that's where we're going to start. A set is simply a collection of objects. And the elements are the individual objects in the set. So it could be something super simple like the set is the songs in your phone. The element are each individual songs. Okay? Be the context in your in your directory, in your phone directory itself. It could be the members of your family. So it can be people. It can be actual objects. It could be things. It could be all your collection of the textbooks that are living in your dorm room. Okay? Any of those things could be called a set. There's a couple of ways that we're going to talk about describing sets. One of them is called the listing or the roster method. So some of those verbal examples I just gave, like the members of your family, that's about the only way we can describe that. I mean, we would write them out in a list. With numbers, we have another way of doing it as well. So let me do an example with numbers so that I can show you two ways of describing a numerical example. All right, so let's say we had this set 7, 8, 9, ... Okay, so this would be the listing or the roster method way of describing this set. Just including a list of all the objects. Of course, if the objects continue on infinity, we put the ... We're all good with that. You look at that, you know exactly what I'm talking about, but it's not a very clean way in some sense of writing it because of the ... All right? Let me show you another method. This is called the set builder method. This is going to be the exact same set. I'm just going to show it to you in another view. So you use these fun curly braces. I don't know how good you are at drawing them. I've gotten pretty decent at it, I think. You're going to put an X and a vertical bar. X greater than or equal to 7. And then we're going to put, just bear with me while I write it. It looks like a curvy E, and it does need to look curvy. That's very technical math term right there, curvy. Does need to look curvy, okay? And then you're going to do an N with 2 lines on the left. So just write it down, and I'm going to tell you what you wrote. Part of this you've seen before. You know what that part is, right? It's an inequality. You've seen those since you were, well, you've probably seen them for a dozen years now, inequalities. Value is greater than 7. And you probably look at this and you agree that that makes sense for that part of it, right? Yeah, these are numbers that are greater than 7. So let's talk about what the rest of the notation that we wrote down means. This right here means it's all values. All x values. This vertical line here means such that, the following conditions apply. These are all the x values where the following conditions apply. The first condition is that it's greater than or equal to 7. And you would probably be tempted to stop there, especially if you were talking with young children. But as soon as decimals enter your vocabulary, that's not enough information. Because we didn't actually want the number 7.5, right? We didn't. So this phrase right here tells us what kinds of numbers we're using. Now, the letter here that I told you is a curvy E. This is an element of. So it's this element information that we just talked about before. Is an element of. It belongs to this set. It's one of these things. And this N are the natural numbers. And we don't say natural as opposed to unnatural. That's not the deal. But natural numbers are the numbers that you naturally learn to count with. What the which means? Such that. I could have written it down. I'll do that. That's how we read it. We say such that. All right, so natural numbers are our counting numbers. They're the numbers that you first start counting with when you're a child, which means the counting numbers or the natural numbers start with the value 1. Now, there was an example in your homework, the very first homework that you did, and it talked about natural or counting numbers. I don't remember its reference. It probably said natural numbers, and some of you included the number 0. And I mentioned it when I gave back the homework, and I said, those don't include 0, right? Natural numbers are the ones you learn to count with. Okay, so let's talk about some of these symbols sort of in a more inclusive way. So we're going to make a list of symbols. We've already referenced one of them. This symbol, what would it mean? What did it mean? Yeah, it means is an element of. And please, please, please do make it look curvy. The ones that look like this, like a boxy E, has scientific notation stuff to go with it. Okay, we're not talking scientific notation, so we don't want to mix up the way that we write our E's in this case, all right? This is an element of. And likewise, what do you think is going to happen if I draw a line through it? Yeah, is not. Excellent. We saw another one, right? This letter, this N with the double line on the left. What were these? Natural numbers. They're also affectionately called the counting numbers. And these are the numbers like 1, 2, 3, ... Okay, so in our world, things get a little bit bigger as we move on in elementary school. So the first thing we encounter are natural numbers before we ever get to elementary school. I mean, right? The kids learn to count, and they say, how old are you? And they say, 2, right? We've got the kids right there. So after, that, at some point somebody says to them, well, what happens if you have 3 apples and you take 3 apples away? And the child says, I don't have any apples. And you're like, what number is that? And the counting numbers are not enough, right? You need another number. What number do you need? You need a 0. And so once you include the number 0, you have what are called the whole numbers. And we will talk at length about whole numbers in chapter 3. So this is just the same as what we had before, plus we include the number 0 as well. And that's all well and good until somebody says, well, what's 3 minus 5? And please, those of you who are going to teach early childhood or elementary, do not tell a child I can't do that. You can. You can take 3 minus 5. Okay? We don't usually do it at a young age, but don't go telling them you can't, because then they get in middle school and they tell their teacher, we can't do that, and they look dumb because you can do that. Okay? So don't say you can't. You can say, we're not talking about that now, we haven't gotten there yet, but don't say we can't. When we do, what kinds of numbers do we get? Negative. And just so that you're referencing this in the right way, that's about 5th grade when kids encounter negative numbers, okay? Now, this one's funny. Negative numbers included, and the positive numbers included both, are the integers, and they are the letter Z. These are integers. And you might be thinking, well, why are we using Z? That doesn't sort of match. I used N for natural and W for whole. Why don't I use I? There's a couple of reasons. One, integers would have to be an I, and irrational would too, and that's sort of problematic. We also use the letter that's a lowercase I to mean complex or imaginary. So we got another I going on. That's not real helpful. But the real reason that we use the Z is because it comes from the Latin word for the word integers. So that's where it's coming from. So integers are positive and negative whole numbers. So the way we usually write that is we put the ... at the beginning, and then I can put like -3, -2, -1, 0, 1, 2, 3, and then I can put my ... on the end to include the rest of them. So these are integers. And integers actually, they usually come up after the next one I'm going to show you, but in some sense, the next one is more encompassing. I mentioned decimals earlier being a sort of a problem. If you're just talking about the numbers that are bigger than 7, 7.5 would be included, and that's not on this list, right? So if you're talking about decimals and fractions, those kinds of numbers, you actually have what are called rational numbers. They're a Q with a line on the left. These are our rational numbers. All right, so rational numbers don't have a very nice way of listing them. I can't just do the dot, dot, dot somewhere. That doesn't work, okay? So the best I can do is to describe them in words. These are all numbers that can be written as a fraction. Now, for those of you who've taken proportional and statistical reasoning, you've done, at least recently, you've done conversion between decimals and fractions, okay? For those of you who haven't, you've done it before. You know that you can take a fraction, turn it into a decimal, and a decimal into a fraction. I'm not going to tell you to do it today, but that's something that can be done. So this obviously includes all decimals and fractions. Like, we're good with that. The other things it includes all the numbers that I've already written down. Think about the number 5. Can you write 5 as a fraction?
Yes.
Sure. How could you write 5 as a fraction? 5 over 1. Or you could be really creative and say like 10 over 2, right? Yeah, you could do that. So we can do all of our whole numbers. We could do the negatives as well, right? Sure, negative 5 would be negative 5 over 1. Nothing wrong with that. How could I write 0 as a fraction? 0 over anything but 0.
Yeah.
That's sort of a weird one. But yeah, 0 over 5. 0 over 52, 0 over negative 357, right? So 0 also has this feature, okay? Maybe feel a little bit funny to write it that way, but it can be done. So any idea why they use the letter Q for rational numbers? Where do you think the Q comes from? It's not Latin this time. It comes from the word quotient. Quotient means division, right? Fractions. So that's where it comes from. So that's sort of the positive reason of why we use Q. The reason that we don't use R is because we use R for the next one. R are our real numbers. So real numbers, again, they include everything that we have talked about above, but they also include irrational numbers. So we're not going to talk specifically about irrational numbers in this class, but irrational numbers are ones you've seen before. I mean, you've seen pi. We do that in geometry, for those of you who've taken geometry. You've seen square roots, right, like square root 2. Right? It doesn't have a closed-ended form. Depending on what other math courses you might have taken in high school, you might have seen the number e. E is also an irrational number. Okay, so all of those would be included inside the real numbers as well. So this would be all rational and irrational numbers. So it includes everything above and a whole lot more. And the reality is that for what we do in most of this class, and then also in proportional and statistical, we don't get that far along the number line. You do encounter some of the irrational number stuff in geometry because we have pi involved. So some of that comes about there. Okay, so we're going to do an example. We're going to talk about this particular set. This says we're going to write the set of natural numbers less than 5 using the listing or roster method and then using set builder notation. So both of these methods use curly braces. So no matter which one you're starting with a curly brace. So if you're doing the listing or roster method, what are you going to write down? Where do we start? 1. Yeah, we start with 1. And where will we stop? 4, because it said less than 5, right? So this is the listing or roster method for this particular set. Super straightforward. You can see all the elements in it. It's very nice. It finishes itself. I have no dot, dot, dots. So this example is not a very good one for using the next method. We're just using it for practice, okay? Set builder notation starts with a curly brace. What comes next in set builder notation? The x and the bar. So this is all values, all x's, such that. And then we need to talk about an inequality. What inequality is present here? You can do x less than 5. What is another option you could do right here? There's another one. You could do less than or equal to 4. Right? The one we did first, the x less than 5, sort of fits the verbal description we started with. But both are technically correct, okay? But you have to be careful, because that would also include negative numbers and fractions and things like that, and that's not the kind of numbers it said. It said what kind of numbers? Natural numbers. So we need to say x is an element of the natural numbers. All right, let's take a look at a couple of unfortunate uses of the English language. Are you ready for that? Mm-hmm. All right, the first phrase is equal sets. Two sets that contain exactly the same elements. And we all said, well, yeah, that sounds about right. Equal sets. They contain the same stuff. All right, one-to-one correspondence. This is a pairing of elements between two sets such that each element of one set is paired with exactly one element of another set. Let me give you a real simple example right here before I turn my slide. You don't necessarily have to write it down, but let's say I had the numbers 1, 2, 3, and I had the letters A, B, C. A one-to-one correspondence means that I can pair them up. If there were a one-to-one correspondence of men and women on OBU campus, that would mean that you could all go out on a date on the same night, and it would not be awkward for anybody. Well, it might be awkward, but not for those reasons, right? There would be a pairing that would actually have happened. Now, here's where the unfortunate usage of the English language comes into place, because for most of us, we probably thought until now that equal and equivalent were the same word. But they aren't in math. Equivalent sets are two sets for which there exists a one-to-one correspondence, i.e., the sets have the same number of elements. So if I call the set on the left with the numbers a set, we'll call it set N for numbers, okay? This is set N. And we call the set on the right L for letters. These two sets are not equal because they have different elements, but they are equivalent because there's a one-to-one correspondence between them. They're not equal, but they are equivalent. I always use the example, I have a brother-in-law, my husband's brother, and he and his wife, their family, they have 4 children, and it's their husband and wife. And that's what my husband and I have. We have 4 children, husband and wife. So if we get together, we could all actually have somebody to talk to or play with, and nobody gets mad because, you know, they're alone. Or there's a group of 3 and somebody gets left out. Right? There's a one-to-one correspondence of people. So we have equivalent sets when we talk about those in our family. Now, sometimes it would be nice for us to see, okay, we have 6 people in our family and they have 6 people in their family. How many different ways could we pair up, right? What are the number of ways that that could happen? So here's my set, 6 people. How many one-to-one correspondences are there that actually exist? Okay, no conditions. You know, it's not like a mom has to talk to a mom. Okay, there's no conditions. It's just how many possible ways could this happen if you did it randomly, right? All right, so here's how I think about it, and this works when we have conditions too, and we'll give an example of that in a second. I have me. That's the line for me. And if my husband's family all comes over, that family in particular, there are 6 different people in that family that I could be paired up with. So I have 6 possible people that I could be corresponded to. Make sense? The next line, that's my husband. How many different people could he be corresponded to after I get my partner? 5. There are only 5 choices left. My oldest son, Temeskin, how many choices does he have? 4. And what are we going to do with my last 3 children as we keep going down the line? 3, 2, 1. The fundamental principle of counting says that the way that we can find out the total number of ways then that this could happen is that we simply multiply all these values together. 6 times 5 times 4 times 3 times 2 times 1. And that will be the total number of correspondences. So what do we get when we multiply that out? If you have a calculator, grab it for me. If you don't, it's okay. Just hold tight. We're going to get it soon. You got it. 720 correspondences. That seems like a lot, right? Okay, I ran out of space for the word. Let's try that again. All right, 720 correspondences. Now, I'm going to sort of put, this is like example 2A, if you will, or 2B. I'm just going to add a condition on here. Okay, so same thing as before. There's 6 people and so forth, all right? And my condition is going to be, what if, by default, this is how it really works, right? What if the moms are in correspondence by default? And same for dads. So there's some conditions on it now, right? I mean, I still have my same 6 lines that I had before. But if the first line is me, how many correspondences do I have? 1. There's only one possible person that I can be talking to, the mom. And how many correspondences are there possible for my husband? 1 for the dad. But then once we get to the kids, what happens? We'd have 4 again, because there were no additional conditions on those, right? So we'd have the 4, 3, 2, 1. And again, we'd multiply them out. And what would we have? Was it? 24? I don't have this one written out. I'm just making it up. So, yeah. Okay, 24 correspondences. Good deal. Okay, so I show you that example because there's going to be some in your notes or in your homework, in your group work, where they do. They put some conditions on some correspondences, and that's how you deal with them. You just deal with the correspondence issues that happen, and then you deal with the other ones as though they don't have any conditions, because they don't. All right, a cardinal number for a set is just the number of elements in the set. So if the set is S, then the number of the cardinal number is n of S. So it looks like this. It just means the number of things in it. So if we were going to write, for example, n of hands, where hands is the people in my family, today, at this current moment, that would say 6. Okay? N of hands is equal to 6. It's just counting how many objects are in there. That's not the set, that's the number of items in the set. A set is called finite when the cardinal number is a whole number. Okay? Finite, you can count it. There's a number that can be ascribed to what you've described. Infinite means that the cardinal number is not a whole number. In particular, we talk about that as being something that's unable to have an ending point, right? It keeps going on forever. Infinite. This is probably my favorite one, the null or the empty set. So if you hear me say empty set or hear me say null set, that's the same thing. This is a set that contains no elements. It has a cardinality of 0, because there's nothing in it. And it has a couple of different ways it can be written. One way is a 0 with a slash through it. So every now and then I have students who like to write their zeros like that. Don't write your zeros like that because we're using that notation to mean something different. Okay? This means null or empty set. Another way to write a null or an empty set is to write curly braces that simply have nothing inside of them. And I always hesitate to write this down, but I'm going to write what you can't write down, and then I want you to make sure you make a big old mark on it like I am, okay? Here's what you cannot write. Whoops. This is not appropriate. So put a big old X over it so that you know you can't write it like that. Okay? Because that's not an empty set. That's a set that contains the empty set. It's a set that is a set. The elements in the set are a set itself. It contains nothing. It's not appropriate to write it inside of itself, okay? So either of those first two notations are perfectly fine. We'll do an example of a null set in a little while later, but before we do, we're going to talk a little bit about cardinal numbers. All right, so we're going to take a look at finding the cardinal number of each set. And so what I'd like for you to do is where I've written the lowercase letters A, B, C, D, just change them to capital letters, and we'll call this set A, set B, set C, and set D. These are our sets. And what we're asked to find is the cardinal number. So notationally, that means we want to find n of A and n of B and n of C and n of D. That's what we're looking for, the number of items each set is talking about. Now we've done some counting arguments. We did it with the Gauss stuff on the first day of class actually. So this isn't brand new on how we do counting, but we might need to remind ourselves how we do it. How would I find the number of items between 9 and 99? Look, they're all there. Nobody's skipping anything. How do I find the number of items from 9 to 99? Good. We do 99 and then we minus 8, the number that comes before the one that we have. 99 minus 8, and that would give me what? 91. So the number of items in set A is 91. Set B is a little different because it skip counts, right? What kinds of numbers is it including? Just the evens. Okay, so how are we going to count the number of items in this set? We will have to divide by 2. Now, because it starts at 2, we don't actually have to do any subtracting. It's the first even number. But let's say for a moment, just for argument's sake, that it didn't have these guys here, right? If it didn't have those guys, what would you do? Well, you would take the number at the end, 2002 in this case, and you'd subtract the number that should have come before it in the pattern. Well, what's the number that comes before 2 in the pattern of even numbers? 0. So technically we are subtracting, even if we don't write it down, we're subtracting 0, which is not a very exciting thing to do, and then we're dividing by 2. So that's what you would do if it didn't start at the beginning, so to speak. 2002 divided by 2 would give me what? 1001. So the number of items in set B is 1001. C and D look weird. Part of why they look weird to you is that they're in set builder notation. We're not as comfortable or familiar with that. So we do have to stop and think about what it's describing a little bit more thoroughly than we did for parts A and B. So let's take a look right here, and let's actually try and write out what we actually have in this set if we were writing it out. This says that we've got all of the items that are x squared, such that x is equal to 1, 3, 5, all the way up to 99. So what in the world are we going to do? What are the elements in this set? Okay, partly odd numbers. That's important. We're going to need to know that in a minute. The odd numbers are natural numbers. That's true. Can somebody give me one number in this set? I'll give you one. 4 is in this set. Why is 4 in this set? Oh, I didn't mean 4. I meant 9. My bad. 9 is in this set. Blah.
Is there a square in them?
Yeah. 1 is also in this set. Because 1 is the same as 1 squared. 3 is not in this set. But 3 squared is, right? That's where I got my 9 a minute ago. And 5 squared is in my set. All the way up to what? 99 squared. So the elements themselves in this set are not the odd numbers. They are the odd numbers squared. Is everybody with me on what the set itself looks like? Now, that's pertinent to the section that we're talking about. It's not particularly pertinent to the answering of this question. But if you're asked what this set actually is, it's the squares of odd numbers, not the odd numbers themselves. Now, what we're asked is how many of them are there? So what would that answer be? We did. We could do the same thing as before. Does it matter that they're squared? No, we're just counting them, right? So counting these objects over here would be the exact same argument as counting the objects down here. Are you with me? The squaring doesn't change how many objects they are. It changes what the objects are, but not how many of them. So if we're taking a look at this, we can really just ignore the fact that they're squared and we can just count the numbers from 1 to 99. So how are we going to do that? Somebody mentioned that they're odds. It doesn't include everything. How are we going to count those numbers? Does anybody know how many there are? There are 50. That's correct. How'd you get 50, Erica?
100 divided by 2.
Okay, so you're right. How did you get 100 divided by 2?
I couldn't divide 99, so I went up to 100 so I could divide it even.
Okay, so there's 2 ways to think about it. That's why I wanted to ask, is because I wanted to see what you had done. One way is to sort of think about what would happen if I had all the numbers there. Well, if I had all the numbers from 1 to 99, I'd have 99 numbers, and that doesn't divide by 2 evenly. That's true. But dividing by 2 is simply removing the evens, correct? I mean, that's why we're dividing by 2. So if I count from 1 to 99 and I remove the evens, I should get the same thing as if I count from 1 to 100 and I remove the evens, because the 100 gets removed. So you could think about it that way, and I think that's kind of where you were coming from. Another option of how to think about it is you could say, I'm going to take the number before 1 in the pattern and subtract. What comes before 1 in this pattern of odd numbers? A -1. If you were looking at this pattern and you were going the other way on the number line, -1 would come before it. And if you did 99 minus -1, what would that give you in the numerator? 100. So that's another way to sort of get to the 100. And of course, either of those divided by 2 give you 50. Okay, either of those perspectives give you 50. Now, the reality is that the numbers from 1 to 99 are a small enough set that you could literally count them. But if we went from 1 to 999, that would not be so very easy to do. Okay? All right, let's take a look at the last one, part D. This says all x such that x is equal to x plus 1, and x is a natural number. So let's do the same thing we tried to do before, right? Let's write down what elements this is. So can somebody give me an example of a number that would be in this set? 2. Okay, so if we think that 2 is in this set, then that means that 2 is equal to 2 plus 1. Is it? No. Okay, so 2 is not in the set. Somebody had one? Erica changed her mind on what she thought. What are you guys thinking?
Anything you try, it's going to be more than that. So.
Okay. So Ariel says, no matter what I pick here, The other side's going to be one more than that. And what? She's right. So what does that mean? There aren't any numbers that do that, right? 0 doesn't even work, right? Because 0 on the left would be 1 on the right. So there are no numbers for which this works. So what does that mean this actually is a set of? This is a null set or an empty set, right? This is what this set actually is. Now make sure you're answering the question asked. The question asked, what is the cardinal number? There is one. It's 0. The cardinal number is just 0. It's not a very exciting cardinal number. Remember, cardinal number just means to count the items that are in it, and certainly there can be 0 items in something.